Welcome back. In this video, we are finishing the lecture of section 1.5, and this is on transformation of functions. We're going to begin by discussing stretches and compressions. If you haven't done so already, please look at the description under the video and find the links for the dynamic worksheets online. It should be the link for the stretches and compressions dynamic worksheet. You can use that if you want to follow along with this example. Now, given a function f of x and a constant a, the function g of x equals a times f of x is either a vertical stretch or vertical compression, while h of x equals f and then the input b multiplied times x is either a horizontal stretch or horizontal compression. If a is greater than 1, then the graph will be stretched. If a is between 0 and 1, then it will be compressed. And again, these are vertical. So that means if we have a graph, we're pulling up and down in these directions, or we're squishing them in. So these are the pulling, the stretches, and the squishing is the compressions. Now, if your a is less than 0, if this constant being multiplied here on the outside of the function is less than 0, then the graph is going to be stretched and compressed using these rules along with a vertical reflection as was discussed in the previous video. Next, what happens with the constant b? So this is the horizontal case. That means we're going squishing things in on the horizon or out, pulling them out, one or the other. If our constant that is multiplied here to the input of the function is greater than 1, the graph will be compressed. Notice that when b is greater than 1, we have a compression versus when a is greater than 1, we have a stretch. If b is between 0 and 1, the graph will be stretched, and again, it's the opposite of this case. And if b is less than 0, we apply the rules as above along with a horizontal reflection as discussed in the previous video. Now I'm going to make some space to go over the dynamic worksheet as an example. Please pull out some scratch paper. As you can see below, I have my scratch paper ready to go. And we're going to examine what happens to the graph when we change values of a and b. We're going to call this blue function g of x, and this one equals a times f of x. And we're naming this function, the green one, h of x, and let that equal f with the input b times x. And unlike the tables we usually make, which give us ordered pairs, each of these outputs is going to be a function. We're going to put in a value for this a constant or this b constant and see what happens to our original function f of x. And remember, f of x equals x cubed in this example. And that is visible right here. So take a moment and play around with this example. You can move the sliders up or down and see what this does to the graph. This button above will refresh. As you can see, I just refreshed and it resets both the sliders to 1 and the viewing window to what we began with. So with that, let's see what happens when we let both a and b equal 1/2. So let's move both sliders down to 1/2. And let's move this slider down to 1/2. Both graphs are a little wider, but they're not quite identical. So what just happened? This one, my little hand would have pushed it down because this is a vertical compression. This one is a horizontal stretch, so the graph got pulled out side by side. So let's write that down. When a equals 1/2, g of x equals 1/2 f of x, which is just 1/2 times x cubed, or you can write this as x cubed over 2. This resulted in a vertical compression. So the graph was squished up and down, squished in the down and in the up direction. When we did this for the graph of h of x, we let b equal 1/2. We end up with h of x equals f with the input of 1/2 times x. So this becomes 1/2 times x quantity cubed, which is 1/2 cubed x cubed, and we can also write this as x cubed over 2 cubed. And this resulted in a horizontal stretch, so out in both the left and right directions. Now let's explore what happens when we let both a and b equal 2. Before we do that, let's fill in our table. When a is 1, we have our graph of just x cubed. When b is 1, our graph again is just x cubed, so the graphs are identical. When a is 1/2, we end up with x cubed over 2. When b is 1/2, we end up with x cubed over 2 cubed. So here we're starting at 1. Let's look at what this looks like again. Here's 1, and I can move this up to 2. I can move this one up to 2. So both graphs are more narrow, but the graph on the right seems a little narrower than the graph on the left. So now let's look at this algebraically. When a equals 2, I end up with g of x equals 2 times f of x equals 2x cubed. This was a stretching by this factor of 2 on the outside, a vertical stretch. Let's do the same thing with b. So when we let b equal 2, we end up with h of x equals f of 2 times x equals 2x cubed equals 2 cubed x cubed. What just happened to the graph? This was compressed horizontally. So compressed inward from the left and right direction. Now that we have looked at vertical stretches and vertical compressions, you can either close out this worksheet or you can spend some more time exploring it. That's up to you. Let's go back to page 17 of our notes for this lecture. The next concept we're going to discuss is functions that are even, odd, or neither. A function f of x is called an even function if for every input x we have f of negative x equals f of x. And this makes an even function. So if you notice, an input of a negative value has no effect on the function, on the output of the function. Even functions are symmetric about the y-axis. In this case, think of something like a parabola. It's symmetric about the y-axis. You can flip it back and forth in these directions and it looks the same. A function f of x is called an odd function if for every input x we have f of negative x equals negative f of x. You notice this does affect our output. Odd functions are symmetric about the origin. This looks like the graph of, say, x cubed. Example 4. Determine whether the following functions are odd, even, or neither. Let's plug in negative x for each of these examples and see what happens. So I have f of negative x equals 2 times negative x cubed plus a negative x, which is equal to 2 times negative x cubed minus x. Now I have negative 2x cubed minus x. Notice that both of these have a negative factor, a negative 1 in common, so we can factor that out. Write this as negative 2x cubed plus x. And look at this, 2x cubed plus x is our original function. So this is simply negative f of x. This tells me this is an odd function. Let's look at example B. G of negative x equals negative x squared. So this is a negative on the outside. A negative x times a negative x is going to be a positive x squared. And we're back to where we started. This is our original function. So since this negative input had no effect on the output, this is an even function. Notice in both of these cases, either every sign of the function changed, so both of these positives became negatives, or none of the signs changed. This negative stayed a negative. Let's see what happens here. For example C. We have h of x equals x cubed plus 4x squared plus 1. Let's plug in our negative x. That's negative x quantity cubed plus 4 negative x squared plus 1. This is negative x cubed plus 4x squared plus 1. This x cubed started off positive, and now it's negative. This 4x squared started off positive, and it stayed positive. Same with this plus 1. So not every sign changed. We cannot rewrite this. This does not equal h of x, and this does not equal negative h of x. So this is neither even nor odd. Finally, let's put together a lot of what we've learned in section 1.5 and translate this graph. There's one quick change to make to this example. Go ahead and change this plus sign to a minus sign on your own notes. And I'm going to sketch this in red to make it really clear that this is an update, and that's mostly to do with the fact that if we shift it, the way this graph is being shifted, if it's positive, we're going to see very little of the graph. It'll end up kind of way up here, and I wanted us to see more of it. I want us to end up kind of down here. So I decided to change this to a negative. Given the graph of f of x equals x squared to the right, so that's this graph right here. This is f of x. Sketch g of x equals 3 times f of x minus 2, quantity, minus 1. So let's start by looking at what this 3 does to our function. So 3 f of x. Let's find some points here. Here's 0, 0, 1, 1, 2, 4, and negative 2, 4. Now let's examine what happens to each of these, and we can do this by just quickly sketching out a table. So here's x and 3f of x. And let's do these key points, negative 2, negative 1, 0, 1, 2. At negative 2, our original function of f of x outputs a 4, and then we multiply that 4 by a 3 to get 12. So that will not be visible on our graph. What happens at negative 1? At negative 1, we end up with a positive 1 output. Multiply that by 3 to get positive 3. 0, so we'd plug in a 0 here, or look at our graph. The output of 0 is just 0, and 0 times anything, including 3, is just going to be 0, so that stays the same. I know that this output, when we enter in 1 and get the output of 1, I'm going to multiply that by 3, and 1 times 3 is 3. So that'll put me up here. Finally, when the input is 2, our output is 4, and we end up with 12 again, since 3 times 4 is 12. Let's sketch out our new points. So I have 0, 0, negative 1, 3, and positive 1, 3. And so what we see here in this light shade of blue is 3 times f of x. Next, let's see what happens when we change our input from x to x minus 2. So 3f of x minus 2. What is that going to do to our graph? So if you recall from a last video, when you see an input change with a plus or minus, this is a horizontal shift, so we're either shifting to the left or to the right, and that depends on whether or not this value is positive. And if you recall, the form is f of x minus h, and when h is greater than 0, we shift right. This 2 is greater than 0, so we shift right. This means that every single point should shift over 2 places. So this point would go over 1, 2, and end up here. This point will shift 1, 2, and end up here. And I'm purposely erasing these arrows to keep my graphs decluttered. And now let's shift this one 1, 2. This ends up here. And we can connect to these dots. So here in purple, we have 3 times f of x minus 2. Finally, let's explore what happens here when we subtract 1. So this is what we're going to explore last. So if I have 3 f of x minus 2 minus 1, what happens to this graph? If you recall, adding or subtracting outside of the input shifts the graph up or down. So from the last video, recall f of x plus h is a vertical shift. And I used h already, so let's use a different variable. Let's say plus m. And in this case, m is less than 0, so we shift down by 1. So let's go ahead and shift this point down by 1. Let's shift this point here down by 1 as well. And let's shift this point here down by 1. Go ahead and connect this. So this graph in pink is our final graph. If you have all of these on your notes, this is fine. When you're working on this, say for a quiz or an exam, I only want to see the final graph, so sketch out any intermediate steps very lightly. As you can see, I now only have the original graph of f of x and then my final version here. This is g of x. If you were working on this assignment as, say, a quiz or an exam, so anything written by hand, this is what I would expect to see as a final answer, the original graph and the shifted graph. If you drew any intermediate steps like we did in the video, say like we did in blue and purple, please do those really lightly. Otherwise, use some method, darken this somehow to emphasize that this is your final answer.